Welcome viewers. In this video we will see the dielectric boundary conditions. There are two boundary conditions available. We will see one by one. What is meant by dielectric boundary? There are two dielectrics are combined together. The line joining these two dielectrics nothing but a boundary. So what happen in this boundary? So when the flux line flowing through a single medium, they are continuous. So for example, if the flux is flowing through a single medium, single dielectric means it will be continuous. There is no disturbance. When they flow through a boundary formed by two different types of dielectric, they got refracted. Suppose if the flux line is flowing from one dielectric material to another dielectric material, there may be a chances of reflection both in magnitude as well as angle. So this can be studied by using boundary condition. So that we are going to, whether there is any change in the flow of flux in magnitude and angle, that we are going to study in this boundary condition. So the surface of glass board, one glass board is available. So this glass board and air is a glass air boundary, because air is also one of the dielectric material. It is available everywhere. So if we consider the glass board, on the surface of the glass board is one boundary. Over that air is available, that is another boundary, that is another dielectric. So the surface of this glass board is a glass air boundary. Now we'll see this boundary condition. First boundary condition. So when the flux lines flowing from one dielectric to another dielectric, what will happen if there is any change in the flux both in magnitude and angle, that we are going to study in this boundary conditions. First we will see the first boundary condition. This first boundary condition, consider a boundary formed by two dielectric as shown in the diagram. By referring this diagram, this line is nothing but a boundary. This line is the boundary. So below that we have dielectric material 1. Above that we have dielectric material 2. This is dielectric material 1, this is dielectric material 2. Both are combined together. That line is nothing but a boundary between first dielectric and second dielectric. We placed one box such that it encloses both the media. It covers both dielectric 2 as well as dielectric 1. The box is placed such that it covers both the media. Half is available at boundary 2, available to dielectric 2, half available in dielectric 1. Here what we are going to see, the displacement density, normal component of displacement density. This is the normal component of displacement density entering into the box, that is in the boundary, that is in the dielectric material 1. But it is leaving at dn2, normal component of displacement density vector, leaving this box at second dielectric material, right? Entering in first dielectric material, leaving in the second dielectric material, so that we will analyze whether both are equal, if there is any change in dn1 and dn2. That is our analysis, because it enter at first dielectric, leaves at second dielectric. The surface area of the box is delta S, the height is delta H, right? The height is delta H, the surface area is delta S. So at this boundary what we have, charged sheet with density sigma coulomb per meter square. So we placed one charged sheet is available. One charged sheet is placed at the boundary, sigma coulomb per meter square. So due to that we will see what will happen in this, whether both are equal or any changes is available. So this description is given. Consider a box at the boundary such that it encloses both the media. So this is the angles are given. This theta 1 is angle of incidence, entering. Theta 2 is the angle of emergence. Emergence means leaving. D1, D2 means normal component. This is the flux displacement density. dn1 means normal component, right? Now we are going to apply the Gauss law to the box. Gauss law. What is Gauss law? Normal component of flux coming out of the charged body is equal to amount of charge enclosed. Right? Flux is equal to charge, pi equal to q. Now we need to identify what is the flux available here, what is the charge available here. Then we can apply the Ampere's law. From that we can find the relation. First we will find the flux. What is the flux? What is the flux entering the box? We have dN1 is available. Normal component of flux density is entering. Then what is flux? D equal to pi by x. Displacement equal to charge per unit area. So from that we cross multiply this. Pi equal to ds. So the flux equal to displacement density into surface area. What is given D in the diagram is displacement density vector, not a displacement density vector. From displacement density vector we can find the flux using this formula, pi equal to ds. So that flux entering the box is dN1 into dx. dN1 is normal component of flux density. Flux means dN1 into ds. Similarly, what is the flux leaving the box? dN2 into ds. Right? dN1 into ds is the flux entering, dN2 into ds is the flux leaving. Then what is the charge enclosed by the box? We have sigma is available. Charged sheet sigma is placed at the boundary. What is sigma? Q divided by S. Charge per unit area. We cross multiply this so that Q equal to sigma into S. Charge equal to charge density into area. Q equal to sigma into S. So that sigma into delta S. What we have? Delta S. Right? So this is flux entering, this is flux leaving, this is the charge available. So what is the Gauss law is given by Gauss law? Net flux is equal to the charge enclosed. What is net flux? Net flux means difference between these two. dN1 minus delta S minus dN2 delta S equal to sigma into delta S. This is the net flux. Flux entering minus flux leaving equal to charge. So the delta S is commonly available. We can cancel the delta S. So dN1 equal minus dN2 equal to sigma. So what we got? This dN1 and dN2 are not equal. That is depends upon the charge. So if any charge is available at the boundary, the fluxes density vectors are not equal. It will differ. That is the relation we have. Right? So that is given here. Normal component of flux density vector is discontinuous by a amount of charge density of the sheet. Right? They are not continuous. What is the flux entering is not flux leaving. There will be some discontinuous available. Why? Due to the charge density. Suppose if the charged sheet is not present at the boundary, right? We assume that the charged sheet is available. Now, if the charged sheet is not available, what will happen? Is sigma equal to 0. So that this value is 0. So dN1 minus dN2 equal to 0. So bring the term in the right hand side so that dN1 equal to dN2. Now both are equal. Flux density vectors are equal when the charge is not available. So if the charge is not available, both are equal. So the flux line flowing from one boundary to one dielectric to another dielectric will be continuous if there is no charges are available. If any charge is available, it will be discontinuous. That is the conclusion we got. If the charge is not available, they are all equal. Right? Now it is given. The statement is given. Normal component of flux density vectors are equal. They are continuous at the boundary provided there is no charged sheet at the boundary. Right? How they become continuous? Only there is no charged sheet at the boundary. Right? From vector diagram we can write this relation d1 cos theta equal to d2 cos theta 2. From the vector diagram we can write this. Now we'll see the second boundary condition. Second boundary condition is dealing about tangential component of electric field. First boundary condition, normal component of displacement density. Now we are going with tangential component of a electric field. Right? You refer this diagram. So this is the first dielectric material. This will be second dielectric material. This line is nothing but a boundary between first dielectric and second dielectric, 1 and 2. We have one closed path, rectangular path, A, B, C, D, A, such that it encloses both the dielectric. A, B available in dielectric 2, C, D available in dielectric 1. So it covers both the dielectric. The height is delta H, length is delta L. So in this AB what we have? ET1, tangential component of electric field intensity ET1. In CD, ET2. See the direction, both are opposite. So this is negative. And see the vector diagram. This is tangential component. This will be normal. Electric field intensity E1 and E2. This is angle of incidence. Theta 2 is angle of emergence. So that is given here. E1 and E2 are electric field intensity in media 1 and 2. ET1 and ET2 are the tangential component of electric field intensity in media 1 and 2. Now we need to verify whether both are equal. ET1 and ET2 are equal. Another thing, there is no charge sheet available. In first boundary condition we placed one charge sheet. Now we are not placed any charge sheet here. Now we'll go to this. Consider a rectangular path ABCDA at the boundary such that it encloses both the media. Right. Static electric field is a conservative field. What is meant by conservative field? Net field is 0. That is integral E dot dl equal to 0. If any closed path is there, the total electric field intensity will be 0. Now we can apply this to the closed path ABCDA. We can apply this condition for ABCDA. So apply this equation to the loop ABCDA with delta H equal to 0. We assume that the delta H is approaching to 0. So integral E dot dl equal to 0 for a closed path ABCDA. So that is written in 4 parts: AB, BC, CD and DA. That is equal to 0. What is the electric field intensity in AB, BC, CD and DA? Now refer the diagram. The electric field intensity AB is ET1 into delta L. CD is ET2 into delta L. What about BC and DA? This delta H is approaching to 0, so the value is 0 here, because height is, we are approaching your height, assuming your height is 0. So we have ET1 into delta L here minus ET2 into delta L. So that is available here. As delta H is approaching to 0, second and fourth terms are tends to 0. The first term AB is ET1 into delta L. Then third term is minus ET2 into delta L. That is equal to 0. So we bring this term right hand side. So ET1 delta L equal to ET2 into delta L. This delta L got cancelled. So ET1 equal to ET2. So tangential component of electric field intensity, the first dielectric, second dielectric, both are equal. Directly we got this relation. Why? Because there is no charge sheet. We are not placed any charge sheet. So straightly we got both are equal. So that is given here. Tangential component of a electric field intensity vectors are equal. We are not having any condition. Directly we got that both are equal. From vector diagram we can write E1 sin theta 1 equal to E2 sin theta 2. E1 sin theta 1 equal to E2 sin theta 2. Similarly we got from first boundary condition also. First boundary condition D1 cos theta equal to D2 cos theta 2. Second boundary condition E1 sin theta 1 equal to E2 sin theta 2. This one displacement density, this one electric field intensity, right? For equation 2 by 1, you give E1 sin theta 1 divided by D1 cos theta 1 equal to E2 sin theta 2 divided by D2 cos theta 2. Right? So that E1 divided by D1 sin theta 1 by cos theta 1 is tan theta 1. Sin theta 2 by cos theta 2 equal to tan theta 2. now we'll substitute this. D equal to epsilon E, the relation is available. So that D1 equal to epsilon naught epsilon R1 into E1. Similarly, D2 equal to epsilon naught epsilon R2 into D2 into E2. Now we'll substitute this. E1 tan theta 1 divided by D1 is replaced by epsilon naught epsilon R1 E1. Then D2 by E2 into tan theta, this D2 is replaced by epsilon naught epsilon R2 into E2, right? So this epsilon naught is available in both, that got cancelled. This E1 is available, that got cancelled. This epsilon R1 is available, epsilon R1 and R2. So tan theta 1 divided by epsilon R1 equal to tan theta divided by epsilon R2, right? The E1 and epsilon naught 1 got cancelled. So from this relation we can write tan theta 1 divided by tan theta 2 equal to epsilon R1 by epsilon R2. So by using this relation we can find the parameter. Suppose theta 1, theta 2, epsilon R1 is known, mean we can find epsilon R2. By using three parameters, the fourth parameter can be calculated, right? So in this we discuss about dielectric boundary condition. There are two boundary conditions available. First boundary condition deals with normal component of displacement density vector. Second boundary condition tangential component of electric field intensity. Finally we got this relation also that can be used to measure the parameters.